The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to Advanced Analytics for Asset Control and Optimization. Our webinar today is with Volaton AI in partnership with Infocast Events. Today I have with me Pavel Romashkin, Artificial Intelligence Consultant at Volaton AI. Today, if you have any questions during our webinar, please type your questions in the Q&A box in the lower right-hand corner of your screen, and we'll make sure to answer your questions if time permits. Thank you so much, and now I'd like to welcome Pavel Romashkin.
Hi everybody, my name is Pavel Romashkin and welcome to our Advanced Analytics for Asset Control and Optimization webinar. I'm currently with Volaton AI, which is a research and development organization also specializing in integration of cutting-edge AI technologies into the energy space. We're also the part of Energize California Innovators Program, which is the California Energy Commission sponsored organization. And among my notable activities in the past before Volaton AI is the work I've done with companies like Google and Accenture and Biotechnologia, where I delivered various AI solutions, and as well was responsible for plant and factory rehabilitation optimization under Kyoto Protocol. Next slide, please. So as we're going to be talking about pretty advanced stuff today, I would like you to have the right mindset for it. And this is Arthur C. Clarke. He is a sci-fi writer who said that any sufficiently advanced technology is indistinguishable from magic. So with that in mind, let's go to the next slide. So let's talk about our agenda. We're going to start with defining industrial artificial intelligence. Then we're going to jump into deep reinforcement learning, which is the core of our discussion today. Then I'm going to show you some of the practical applications and the results that were achieved by using this technology, and as well as cover the research frontiers. I also have one slide on how to get started with all this stuff if you're interested. All right, next slide, please. So as we're talking about industrial artificial intelligence, we need to talk about complexity. And in the format of industrial artificial intelligence, the complexity is defined by millions of devices talking to each other in a nonlinear way. Such systems are usually pretty hard to model, and we often have to make expensive simplifications in order to achieve some acceptable results. Also, the models we design for this complexity have to work with noisy inputs under diverse conditions. So one example of such a complex system could be our current energy transition from large fossil fuel generation to distributed and renewable energy. Such transition results in increased uncertainty and complexity in both business transactions and also the physical flow of electricity on the grid itself. In such complex system, it's really hard to predict the activity of each component of this system. By studying and modeling this component alone, you actually have to look at the whole system in order to do proper modeling. And also, even if we have really high data for these systems, it's some performance metrics are just hard to optimize for. So next slide, please. As we're going to be talking about industrial artificial intelligence, we need to define what we're going to be applying it to. So the scope for industrial AI is any physical operation that could be modeled as a sequential decision-making problem with the goal of removing manual labor and also improving productivity, efficiency, and performance. So the sequential decision-making framework is the framework under which we make decisions after receiving feedback from the previous decision. So it's kind of like step by step. And some examples of systems where this is applicable are supply chain management, autonomous vehicles, factories, smart cities, grids, and so yeah, that sort of thing. Next slide, please. Of course, when we're talking about industrial artificial intelligence, we're talking about optimization. In fact, optimization is the core of artificial intelligence as we know it today. So, for example, let's look at the problem faced by a grid operator who wants to model optimal asset exploitation, right? He tries to solve the greatest dilemma, essentially. So today, for him to be able to solve this, he needs to look at the the grid that contains various components such as the electrical storage, solar farms, wind farms, critical systems like hospitals, energy-consuming systems like energy-intense systems like factories, and we have office buildings, and we also need to include more classical power generation, and it all needs to be somehow controlled. So basically, it's a system with different loads and generations. So in order to solve optimality in a system like this, we usually use abstract models and fuzzy logic. But those systems can't capture the complexity of interactions in such system. And the process today is usually to design, like have a team of engineers design some clever heuristics, and then test and tune, painstakingly, I should say, test and tune them until we get some practical performance. And the problem becomes even more complicated due to older and obsolete technologies used in the energy sector today. So intelligent network optimization, it's not only desired, but it also mandatory and in fact beneficial in order to stay competitive under the forces of disruption that we're experiencing today. By our estimates, a company could look for 30% of CapEx savings and 10% of OpEx savings with such systems. Next slide, please. So as we're going to be talking about industrial artificial intelligence, we need to highlight major trends that are happening right now. So there are 4 of them. So the first one is interdependency. We're seeing that virtually much of the energy sector parts are becoming more interdependent with different sectors such as material flows, transportation, and financial markets. Also, as we mentioned before, we have new and diverse sources of energy entering the space. And in fact, legislation is encouraging that as well by proposing different bills. Like, for example, in California, the SB100 proposal wants to make California 100% renewable, like filled by 100% renewable by 2030, which is not that far, in fact. This is possible. There were studies done that we can actually, in fact, have 100% renewable energy, but that will require advanced analytics that can go from just observing the space to actually making decisions in that space. And of course, we have to look for efficiency improvements, because the compound losses from the raw energy to the electricity in our sockets is pretty high, and essentially every optimization we can have will matter a lot. Next slide, please. So let's talk about enablers. Pretty much everything that's labeled as smart, like smart cities, smart factories, or industrial Internet of Things, they require a lot of data. And in fact, artificial intelligence just won't work without a huge amount of data. And IoT is one of the enabling industries for industrial artificial intelligence. It also may be known as Industry 4.0. With a compound aggregate growth rate of 15.6%, we're looking for it to achieve about $1.29 trillion in 2020. So to illustrate why companies need to invest in gathering more data, I provided this kind of like an example. On the bottom right, you see 3 different pictures. And the first blurry picture represents some data collection. Maybe you can see some of the characteristics of the picture, but it's not well defined. And as you collect more and more data, you get to see more details, and maybe you see colors, and kind of the comparison is that you can actually see a better picture the more data you have. Also, it's not only beneficial, but we can actually take advantage of a lot of data these days. So on the top is a chart of the algorithm performance versus the data volume provided to it. And the classical machine learning algorithms actually didn't benefit from increased amount of data. So as you give it more and more data, it just stalls and it doesn't improve your performance really. Deep learning and the neural networks, they actually do. Like, the more data you give them, the better they perform, which is really beneficial for our use case. Next slide, please. So let's talk about actually reinforcement learning. Like, that's the core of discussion. That's the advanced analytics part. Reinforcement learning has been around for a while, actually, 3 decades, and we had it in science. And It could be considered a heuristic form of dynamic programming, which was introduced by Richard Ellman about 60 years ago. But reinforcement learning algorithms weren't really useful due to the curse of dimensionality. Essentially what it means, they weren't able to solve complex problems. But this changed in 2015 after the team from DeepMind successfully combined reinforcement learning with deep learning. And what that allowed is it's allowed for it to do such breakthroughs as play Go. Maybe you heard of AlphaGo match. They used it for reducing the cooling system demand on our data centers and things like that. So what is reinforcement learning? As you can see on the picture, we have the agent environment, and reinforcement learning deals with the agent that learns to make better decisions from interacting with the environment. It starts by knowing nothing about the task, and then it makes a decision. It looks at the reward the environment provides to it, and this way it learns to achieve the objective of any task you give it, defined by the reward function. To give you an example, let's say you want to train a dog to sit. And if you want to model this problem of training the dog to sit as the reinforcement learning problem, you would be the environment and the dog would be the agent. Let's say you as environment, you assume the state of sit, you say sit. Now the dog as the agent has to somehow respond to the state. If the dog in fact does sit, you can reward it by giving it a treat. So the dog receives +1 treat. So now it knows then when you state is sit, it better sit, then it's going to lead to a reward. Or if it doesn't sit, you may withhold the reward, and this way it doesn't get rewarded for this behavior. So what it does is it maps situations to actions. And the reinforcement learning or deep reinforcement learning is still being studied, but there are some applications that we can actually use it for, and it's mature enough for it. So for example, the gaming, the robotics, and the control engineering. The deep learning is the part that allows us to solve our complex problems of millions of states and actions. And the importance of reinforcement learning is well highlighted by a quote from a leading reinforcement learning researcher, Sergey Levin, who said that the reinforcement learning problem is the AI problem. So essentially, if you solve reinforcement learning, you solve artificial intelligence. Why it matters now? Why should we actually look into this today? Well, there are 3 breakthroughs that allow for it. The first one is that deep learning allows us to create expressive high-capacity models that can solve our problems. Also, reinforcement learning algorithms, the breakthrough in reinforcement learning algorithms, can scale with our requirements, so we can actually use it for practical things, not just playing games. And the advances in computer power allows us to train those models in a time frame that's practical for real-life applications. And some of the things it can do, there are some examples on top, like the classical problems where you have this cart and it has a pole, and the idea is you need to balance the forces left and right on the cart in order to keep the pole in a vertical position. Then this one is the bot by OpenAI that learns how to stack cubes by learning from a demonstration into virtual reality. So the agent would put the glasses, it would stack the cube, the robot would learn by just analyzing the images, and then it would repeat the task. And of course, the AlphaGo, the DeepMind's AlphaGo victory, which was pretty successful. Let's go to the next slide. So the landscape of deep reinforcement learning today. Well, first of all, let's look at what the Gartner has to say about it. They say they experienced a 500% increase in calls, and from the companies and from their clients asking about some aspects of artificial intelligence. So it's coming, and they say that about 59% of companies are still gathering the information, and the rest made some progress in pilot applications of reinforcement learning. As you can see on their chart, they put deep reinforcement learning in kind of the innovation trigger stage, and there's still going to be people inflated expectations, and that sort of thing. But I think for control engineering, we can actually try to surpass this inflation and go straight to more or less practical applications. And I'll demonstrate later why that's so. So how deep learning has progressed since the initial discovery in 2015. Let's look at the chart on the left. As you can see, there is a there is a kind of like in the core in the middle, there's a DQN, which is the algorithm invented by DeepMind. And all the little nodes coming out are different algorithms that can solve different games, or they can play different games with some rate of success. And why studying games is important is, well, let's look at some of the characteristics of the games they play. For example, the arcade games, they require fast reaction, precise timing, prioritization of key occurring events. Or racing games, where the agent receives continuous input signal, for example, steering, and it needs to control the position of the vehicle, adjust the braking acceleration, using really fine-tuned control signals. Also, if we have things like fuel or damage, or maybe if there are speed boosts available to the agent, it requires some long-term planning. Also, if the other vehicles are present on the track, there is a moment of adversarial planning. So now we need to plan against the other players. And if those players have damage to the vehicles and they have the speed boost, that involves adversarial planning with some hidden information from the opponents. So there are different algorithms that can actually play things like first-person shooters, open world games, real-time strategies. Now, one of the latest newsmakers in that sense is the algorithm that can play Dota 2, which is a one-on-one multiplayer strategy game. And it's been pretty successful at winning in that game, different players. But to highlight how some of these algorithms measure with the human performer, let's look at the algorithm called Unreal. Unreal can achieve about 900% improvement over what human can achieve in a set of standard Atari games. So it's doing pretty well. Next slide, please. So what has allowed this kind of the breakthrough? Well, it's end-to-end learning. What is end-to-end learning? If we look at the modern algorithms, they can actually output more complex things. They don't just output like a class saying like, oh, it's, you know, dog or cat. They can generate images from scratch. They can create captions. They can create audio. So all these things are thanks to end-to-end learning, where the engineers working with the algorithm can skip feature engineering. And what they need to do, they just can map raw inputs to outputs. You're saying, for example, if you have, you know, this sort of picture, caption it like this, and then it will be able to generalize over different states. Why that's beneficial? Let's look at how usually we solve some of the problems with you know, more standard algorithms. For example, for optimal power flow, we would have stages, for example, like state estimation, then model prediction, then planning, and then low-level control. With deep reinforcement learning, deep learning in general, we can just give it the state, saying, well, that's what it is right now. And we can show it what kind of actions we would like to take, or we can take actions on its own and actually learn from it. Also, different kind of advantages and disadvantages is we can see that optimum power flow solvers are pretty simplistic. They do commit to decisions upfront, and they can't actually guarantee optimal performance. They do approximations. They're also limited to approximation of the plant, and they don't handle the bilinear properties of energy balance. When deep reinforcement learning, it learns directly from experience in the energy system. It receives the inputs, and that's the ground for learning. There are no models involved. It does make decisions one at a time, so it can change rapidly. It handles well non-linearity, and if we want, we can actually program it to do both technical and economical analysis at the same time. And as I mentioned already, that does automatic feature engineering. Next slide, please. Of course, when we're talking about applying deep reinforcement learning to critical systems, we need to take some care. And first of all, we want to make sure it's safe. There are ways to achieve it. Obviously, it's not straightforward, but we need to foolproof the outputs. That an algorithm won't be able to do things we absolutely don't want it to do. We want to pre-train it on historical data, and in general, we just need to manage risks in a responsible fashion. In fact, we can actually include safety as the part of the reward function. So when it's going to be making decisions, it's going to be rewarded for the safe decisions, not maybe the most optimal decisions. Talking about critical systems, here's one example how people were applying it in finance. They were able to achieve a 4-fold return in 50 days on the backtest. with a pretty high rate of 0.25 commissions. So that's pretty impressive results. I couldn't find any other examples in financial systems because I think they're pretty classified, but it shows us what it can do if it's let to experiment and explore the environment. Next slide, please. So what would be the environment and reward for these sort of things? Well, when we think of the environment for this deep reinforcement learning agent, the very important property to remember is the Markov property, which means that our decisions are only affected by the current state. So we're not going to be considering some state in the past. We say that whatever we want to make decision of is in our current state. It's kind of similar to the technical analysis of stock markets, right? When we have the price and we say, well, everything we need to know about the company is in the price already. So we can just make decisions based on that. Of course, it's pretty unrealistic. So it requires us to have the states to be fully observable. But that's not a limitation because we can actually work around it by using partially observable scenarios, where an agent would receive observation and a distribution that depends on the current state and the previous action. So in fact, there's a workaround. How would we actually build it in a technical architecture? Well, the good example is on the top left corner. We would have a two-tier approach where one part would be the learning module and the other part would be the execution module. And the benefits of such approach is that we can do the training and from the historic data or by maybe an operator. We can run simulations on our trained model, and we can do various scenarios, for example, to verify that it actually works. When I say simulation model, it's not the model that we create by hand or with engineers. It's actually the model that the agent learned. Basically, we kind of put it in a container and let it. We can kind of do safely experiments with it to see how it holds. And also in that case, it works as the virtual assistant really to the human operator, because the human operator would be able to train it or would be able to take a suggestion from it, not necessarily let it control the environment directly. But of course, there is an option of direct control as well. If we want to model the energy system in terms of the states, well, some example could be the one in the middle, where we have normal state, alert state, emergency state, failure, or restorative state. And the important part here, well, actually, let me explain what the E and I stand for. So E is equality of generation load demand balance, and the I stands for inequality of physical limitations. They're usually defined through the voltage current magnitudes on active and reactive power that the system can sustain without damage. The important part of this thing is that we can actually model any time frame. So for example, if we want to do scheduling day by day, we can do this, or we can do a millisecond range, which is useful for some situations. Now, when we're going to be working with the reward function, one important thing to remember is what's called the Cobra effect. The example of a Cobra effect happened, for example, in Hanoi, when the government paid to rat catchers to catch rats, and they would pay them based on the tails of the rat. Well, what the rat catchers started doing, they started to cut off their tails and just sell the tails and let the rat run away so they can produce more rats. Reinforcement learning does exactly the same thing, essentially. It doesn't go through the process, it just goes directly to the reward. So when we define the rewards, we need to make sure we encourage the right things, right? Because it's gonna cut corners essentially to get to that state. Another important design consideration is called concept network. And concept network allows us to break certain actions into sub-actions. For example, if we want to train the machine to take cubes from one table and stack them on the other table, we can break it into different sort of like agents. They're going to be doing reaching and grasping and moving and stacking. So each of these agents is its own deep reinforcement learning agent. And that's very crucial for real industrial applications, because in this sense, we can have a team of engineers working on their particular action they want to train the agent, and we can mix and match those, and we can transfer them to different use cases. Like you don't necessarily do one, but you do many. And it also improves explainability. If you want to know why a certain action was done, we can just see which module was activated to do this action. Keep in mind, this is not the same thing as the future engineering we covered before. So the future engineering, you define the heuristic features to say, well, the predicting this thing would require having maybe this parameter, this parameter, this parameter. In this case, it's just the actions being broken down, and each action is still learned end-to-end by deep reinforcement learning. Let's go to the next page. Next slide. All right, time for the first practical example, and this one is for energy optimization. So in this example, this is from the paper by Elena Mucano, called Online Building Energy Optimization Using Deep Reinforcement Learning. What they've tried to do here is they tried to optimize schedules for building energy management system in online fashion. So, like actively right now instead of pre-committing to actions. They verified it based on a highly dimensional Beacons3 dataset, and this dataset contains data for PV generation, electrical vehicle charging, different appliances. It's a very high dimensional dataset. So the idea for this study was that we can actually train deep reinforcement learning agent to reconcile differences between our usage patterns and a variable supply like wind and solar. So how did it work? They wanted to see, they wanted to define success by the cost. I want to make sure that our cost is going to go down. There are already some algorithms that can be used for it, as we mentioned before, like, for example, a particle swarm optimization or game theory or fuzzy methods. But those methods have actually to recalculate every possible solution in order to pick the best one. So it's not very efficient and it's time consuming. Deep reinforcement learning can minimize cost in the newly situations because it has the ability to generalize for situations. So for example, if it's seen something similar to the situation, it can just say that maybe this one is pretty much the same and they only take milliseconds to adjust. It doesn't take the whole recalculation cycle. How they modeled it, because remember we talked about the environment and the agent. So here, the states that environment had were consumption, like load, PV generation, EV generation, maybe the use of appliances, and the price of electricity. The actions were just start and stop. Essentially, it would start the AC, or it would let the people charge the EV vehicles, it would turn on the dishwasher and stuff like that. And the reward was a little interesting. They didn't do it as the actions progressed. The reward was the energy cost, was the energy consumption and the cost at the end of the day. So the results they were able to achieve is pretty impressive. They tested two different algorithms, and the best performing one cut cost, as you can see, for about 26.3% for the peak load, and the cost with 27.4%. So it's basically almost 1/4 of reduction of cost in the peak demand, which I say pretty impressive. Next slide, please. The other one is really interesting. So this one is for a microgrid. It's called Deep Reinforcement Learning Solutions for Energy Microgrid Management. And it comes to us from the paper by Francis Lavet from Belgium, actually. It's the European Union paper. So what this paper is about, what they wanted to do is they want to see if they can efficiently operate storage devices in microgrid that has both solar panels, short-term batteries, and longer-term hydrogen storage. And in this case, the difference between the short-term and the long-term is just the price, right? Like the batteries are more expensive than the hydrogen cells. And this microgrid is not connected to any grid. It has to live on its own, so it's isolated. The problem with microgrids is that they face what's called the dual stochastic deterministic structure. And what it means is that the production, future electricity production consumption patterns are stochastic. We cannot certainly say what they're going to be in the future. But when we change our actions, when we change our storage management actions, they react pretty deterministically. So if you want to discharge the battery, you would probably expect it to discharge as much as you tell it to discharge. For this particular problem, they modeled states as the amount of storage and the storage sizing. They modeled action as the amount of energy transferred in and out of the system. And the reward was just instantaneous operational revenue. So compared to the previous paper, it wasn't like at the end of the day. This one, it was instantaneously. As we make the decision, we get the reward in terms of the costs. They used the base parameters of the battery being 15 kilovolt an hour. Hydrogen peak was 1.1 kilowatt, and the solar peak was 12 kilowatts peak. They ran the base scenario. Again, as we remember, the base scenario means the agent doesn't know anything and it has to learn by just experimenting in the environment. So what the agent figured out to do is it would actually charge this short-term storage from the long-term storage during the night. So it'll be able to meet the future fluctuations of the day. And then during the day, it would just charge everything. Base scenario could actually be improved if we add additional data like seasonality or maybe the day of the week, or like different stuff. You can actually give it. The more data you give it, the better it performs. And what they've noticed is that let's look first on the operational revenue chart. As you can see, what the percentages mean is on the bottom is essentially the scale of the base scenario. So, for example, we had the parameters like battery being 15 kilowatt an hour. The new like 70% would be 70% of that. So the smaller the grid gets, we see that we get a bigger dispersion in revenues. And why is that? Is because the operations are actually more challenging with a small grid. So you make an action and it has a bigger impact than you have a bigger grid or bigger storage sizing. But nevertheless, we can see that the bottom line is a naive policy score, is when the policy would just have the storage and that's all. And then as we add additional data, we see that it actually makes profit, essentially. Like the reward goes about zero though for operational revenues. They also plotted the LEC, which is the levelized energy cost. Essentially, it's the cost of operating the grid through the whole lifetime of it. And to model this one, we take operational revenue as a constant, and the operational revenues were coming from this prediction of the model. As you can see, again, it does pretty well. I think it's average about 25% again of improvement in both revenues and LEC. So why is that important? Is because again of deep learning, where we can generalize solar states, right? And those are the results. Next slide, please. So a little bit of research frontiers. In the interest of time, I'm going to keep it short, but just going to give you an idea of what people are working on and what's still required. Well, I would say still required, but it will be a nice addition to what we have right now. The first one is imitation learning. And in imitation learning, we would like our robots or our agents to learn from example fast. They can learn from example now, but we want to have it sort of like a one shot where you just show it once and it can do it, just repeat itself, right? And we're not talking about the programming ones, right? We have the factory robots that being kind of programmed by an expert and they just repeats the same thing, actually be able to reason about what needs to be done. So there's a paper by OpenAI, and here they do one-shot imitation learning. And actually, I think I've shown this example already. What they do is the person wearing VR headset does a demonstration. The robot learns from pixels, and it repeats the demonstration in real time. Essentially, it learns how to do this, like how to stack robots the way it's shown, which is important because we can train faster. The next slide, please. So another important topic is the transfer learning. Usually humans learn pretty fast. Why? Because we rely on our past knowledge. When we learn a new concept, we already have some baselines for it. For deep reinforcement learning, it's still a problem, and the reason why is that we're not sure how to actually encode the knowledge. For example, for convolutional neural networks that deal with the images, they're already transferable because you can actually transfer the low-level features from one network to another network. So the cost of implementing new visual recognition features is pretty low compared to anything else. For transfer learning, again, it's still an open research topic. There wasn't much progress done, but that's another important research frontier that's happening right now, and the one that's really related to energy space. That if there's a breakthrough, we're all going to benefit from it immensely. Next slide, please. So in terms of how actually to get started with this stuff, well, the common advice is to actually start with the pilot projects. And the pilot projects should be really carefully considered in terms of the costs and risks. And we need to pick the one that's going to have the most impact on the system. Obviously, you need to have the right experience to do this. And you need to think of artificial intelligence as just being a part of your infrastructure. Like when you buy an artificial intelligence, you're not actually buying some like magic, right? Even though the code in the beginning said magic. What you're buying is that's a piece of software that integrates with your upstream and downstream systems, just like your accounting software maybe, or your supply chain management software. It works pretty much the same way. You need to have the inputs, the outputs, and integrates with the whole thing, and you work with it. How we can help? Just quick spiel is that we have some prepackaged solutions we can deploy quickly. It would require some adjustments to the particular use case that you want to do, but it will let you experiment with the reinforcement learning algorithms and see how they perform for your particular use case. We're also looking at the feasibility studies and training and integration and development. So with that, next slide, please. That's it for me. Thank you very much for listening. And yeah.
Thank you so much, Pavel, for your presentation. If anyone has any questions, now is the time. So don't forget to go to the Q&A box in the lower right-hand corner of your screen. And I'll just ask you a kind of general question, Pavel, as people are asking their questions. But you talked a lot about deep reinforcement learning. Why do you think it's important for the AI industry to use that application?
Well, it's not that it's important, it's crucial, right? As we remember the quote by Sergey Levin is that reinforcement learning problem is the AI problem. And the reason being is that so far this is the only way we know to model behavior. And if we wanted to teach artificial intelligence to actually behave within the systems, they need to be able to have the framework for mathematically describe this behavior. And you won't be able to teach an agent to actually do anything unless you have this kind of framework. And that's the one that was the most successful and pretty much the only one on the market right now.
Got it. Thank you so much. And as we're still, if anyone has any questions, please feel free to put them in the Q&A box. I think just generally, what do you see happening in the future for the AI industry? What do you think's to come?
Oh, well, in energy, as I mentioned, right, we need to deal with the complexity. So that's going to be important because, as we go forward, it just becomes more and more harder to actually model it, and we need to have this efficiency. So, that part will be really important. In terms of the general artificial intelligence, I think there are a lot of companies, they try to advertise that they be able to solve the general intelligence, which is basically the problem that can be applied to anything, right? And we'll be able to solve it. I think we're still far from it in terms of prediction. Same with NLPs. I noticed that a lot of the language processing software and artificial intelligence is not performant right now, even though it does have some hopes. Like, for example, people are betting on it being able to process contracts. But from what I've seen, those things are not that smart yet. Yeah, there's so many things you can do, but this one is the most relevant to energy space, in my opinion.
Thank you. Okay, so we have a question here. Dimitrios asks, what do you think is the additional value of deep reinforcement learning with respect to traditional optimization approaches in the context of electrical power systems?
Yeah, sure. So as I mentioned, is that when we're learning with deep reinforcement learning, it gets the signal directly from the environment, right? And when we do traditional ones, we model the environment by some abstract rules and fuzzy logic. And those things are not, at least from my experience, they don't really well do with nonlinear environments, where the energy balance is actually bilinear, right? And deep reinforcement learning can handle those pretty well. And that's the additional benefit, that we don't need to commit right away. We have this ability to do bilinear modeling directly from the energy assets, not from the features that we've chosen for it.
Great, thank you so much for your answer. We'll just wait one moment, see if anyone else has any questions. We appreciate any questions you guys might have. And it looks like that's all for today, but just wanted to say thank you so much. Thank you to Pavel for this excellent presentation, and thank you to our audience for tuning in. Just a reminder, you will receive an email with the recording of this webinar in 24 hours. And if you're interested, for more information of our InfoCast webinars, please visit infocastinc.com. That's infocastinc.com, and make sure to connect with Pavel and Volatent AI. So thank you so much. Is there anything else you'd like to say, Pavel, as we head on out?
No, thanks guys so much. If you have any questions, I think there's my email on the slides as well, so feel free to shoot and we can talk. And have a good day.
All right, thank you so much. Have a great day, guys.